Hi, I'm Ben-Yaakov. This presentation is entitled Current Sharing of Parallel Connected MOSFET Defects. Now, why do we need to connect transistors in parallel? Well, the obvious reason is that if a single transistor is insufficient to carry the current heating up, then we can use two or more transistors in parallel in order to split the current and divide it between the parallel units. For example, I'm showing here two transistors, a boost converter, and in this case we have the two transistors. While they are on, they are represented by a resistor, RD is on, and the idea is that the current coming here while the transistors are on will be split and hopefully evenly between these two elements. Now, we have to distinguish between static and dynamic current sharing. While the transistors are being switched on and off, there are some transients involved which depend on the leakage inductances, capacitances, the type of drive, the turn on time, turn off time, many other parameters. So consequently, we may have a difference in the current through the transistors while switching. So this will be more the dynamic current sharing. On the other hand, once this state of this transition is over, we're talking about static current sharing, and I'm going to talk in this presentation about the static current sharing. This dynamic is for a short time, of course, depending on the type of transistor. It is very important to realize that despite the notion of current sharing is not the goal. This is not what is important. What is important is to have a equal junction temperature between the devices, because this is the limiting factor of a device. And as the power goes up, the temperature of the junction goes up, and you like all the devices to be at the same temperature. This does not necessarily mean that the current have to be the same. It really depends on the situation. And this is what we are going to see. So first of all, let's remember that what we want is an equal junction temperature. This would be our target. And the more are the temperature equal, the better is the case, because otherwise we cannot utilize the transistor to the fullest. Now, in a simplistic explanation, we are saying that a good current sharing, or as I said, which leads or should lead to an equal temperature between the junction, is a positive temperature coefficient of RDS on. And the argument goes like that. If you have two devices, say this one has a lower resistance. Here's this one, and this one has a higher resistance. So as the current builds up, the one with the lowest resistance will have the highest current, while the one with the highest resistance will have a lower current. Now, as the current is increasing, the devices are getting hot, temperature goes up. So since the current here is higher, the temperature here will become higher. So therefore, the resistance will go up, and as more than the other side, and as a result, the current will sort of taper down, and eventually, hopefully, both of them will be equal or very close one to the other. So for good current sharing, we would like to have a temperature coefficient which is positive with temperature. A negative temperature coefficient could be disastrous, because you might have a runaway problem in which the one with the lowest resistance will get, the resistance will get lower and lower, and there will be a runaway. So this is what we'd like to have, and this is the explanation. As I'll show, the situation is much more complex. and just the hand-waving explanation is just insufficient. You really have to go into the details, and in fact you have to build either analytical or simulation model in order to understand what's going on in a given situation. So let's see first of all how is the RDS(on) behaving. I am showing here 3 transistors which are like front technology of today. We have a GaN transistor, it's a VZIC, this part number. We have 2 silicon carbide transistors, and we see here we have a positive coefficient. On the one hand, we don't like it because a positive coefficient means that or a large or relatively large temperature coefficient would mean that the resistance is going up with temperature. It starts at 20 degrees at 22, and at say 120, it's 50% higher, something like that. Now, on the one hand, we don't want the resistance to change. On the other hand, it's good for current sharing. Now, the silicon carbide has a it has a moderate change, and you see this is for one particular device, and I just noticed that they have 2 curves for 2 currents, and indeed for all devices, and this is an information that is not always given, the resistance RDS(on) is a function of the current. And in this case, this particular ST device, they are giving this information. Here it's sort of hidden, but here it's nicely given. And what we see here is if the current is going up, the resistance is also going up. Again, this will be for one temperature, so this is not a complete picture. Here we see that the difference is larger at lower temperature between the current. And as the temperature goes up, the difference becomes smaller. So it's really a complex situation, and there isn't enough information in the datasheet to cover all the parameters from all the aspects. So we're going to do what we can with available information from the datasheet, and I'm going to neglect at this point the change of the RDS(on) with the current. I just assume that it is a function of temperature, period. And of course, the change with current is a refinement that one can add. Now, we see that for the silicon, the situation is, well, not very well for current sharing. You see here you have sort of a negative temperature coefficient, a little bit at lower temperature. Maybe this is not a typical operating temperature, but still units should operate also at low temperature. But then at higher temperature, it's becoming suddenly positive, as we see it here. So what is determining the temperature of the junction that will in turn determine the RDS(on). RDS(on) is a function of the junction temperature. So the simplest way to represent the situation is by this equivalent circuit. In this equivalent circuit, temperature is sort of modeled or mimicked by voltage, and then power by current. That is, voltage represents temperature and current power. So we have here a source of power. This is the dissipation of the device itself. In the case of a MOSFET, in the tunnel. Now, we have then the terminal resistances. These are in terms of degrees per watt, terminal resistances. And then we have the ambient temperature, temperature being represented by a voltage source. Now, obviously, as I didn't write it down, the terminal resistance is represented by a resistance, okay, an electrical resistance. So we have the power actually moving from the junction outside to the ambient through the junction to case thermal coefficient. Then we have the case to heatsink. This could be some grease or something, or maybe some insulator. And then we have from heatsink to the ambient. Now the power is passing through all these and developing a voltage drop, which is temperature. So the junction temperature is the ambient plus the temperature drop on these devices. So we have temperature of the junction is the power going through all these, and then plus the ambient temperature, which is sort of modulating everything up and down. So now we have a curve for the RDS on as a function of temperature, and I have sort of approximated it by a linear relationship of this nature, a linear curve. I see that I'm actually missing here something, so let me add it here. It should be, of course, multiplied by temperature. So we have a sort of an offset plus this is the slope times temperature. This is this curve here. However, current through RDS on is not the only source of power dissipation in the transistor. In fact, in many applications, this could be the smallest part. Another part is the switching losses. The switching losses depend on many things, on the voltage, on the current. And here we see switching losses of, this is the GAN device, the one that I've mentioned earlier. This is the turn off, this is the turn on losses, and this is the total switching losses. These are now energy per switching, okay? A pair of switching on and off, the total, okay? Now this is a function of the current, and all this picture is for a given temperature. It's not written here, but I suppose it's 400 volt, okay? As the voltage goes up and down, of course, this will change. Now this actually summarizes two losses, maybe more than two, but at least two losses. One is the overlap of current and voltage as the device is switching. That's number one. But then there is the capacitor, the output capacitor, which is being dumped as this transistor is switched on, and this also adds to the dissipation. Now this curve is apparently for 25 degrees. Now we don't know exactly what's happening here as the temperature is changing, and it's definitely changing. So as I've already said, there isn't much information, or there isn't the full information for the losses and the so on, etc. So we're going to get by with whatever we have. And so we are now approximating the power, the total power loss of the transistor as the part of the current times RDS on, I square RDS on, times the duty cycle, of course. And I'll assume in this discussion that this is a continuous current, like duty cycle is 1, otherwise you have to include it. And then we have the energy per switching cycle, on and off, turn on, turn off, times frequency. This is energy times frequency is power. So this will be the equation for the total device power. So here's the model that we have. We have a current. I'm assuming 2 transistors just for simplicity. They have some RDS on which are different to begin with, although the same temperature behavior. RDS on is a function of the current and temperature. And then we have the power dissipation. Total power dissipation is also a function of the current, which is affecting RDS on and frequency. And then the temperature of the junction. It's a function of the total power dissipated in the device. So this is the model. Now I'm going to show now how to solve these equations. These are equations you can write down and you can solve it by, these are nonlinear equations, but you can solve it by MATLAB. But I'm going to show how to do it with simulation, and in particular with PSpice. First thing I like to show is how do we model a variable or a resistor which depends on something, okay? Now, the way to do it is, this is a resistor which is controllable or changing or variable, and the way to do it is to replace it by a current source defined by the voltage across the device times this R. Now, if R is constant, then definitely the current is V over R, so this is a fixed resistor. But if R is a function of other things, for example, in our case, the current, the power, whatever, then it'll become a variable resistor depending on the value of this element here. So let's go now and see how we can model the case, simulate it, of two transistors connected in parallel with a constant current, assuming that they are switching with a certain duty cycle, but for the dissipation of the transistor, I'm not going to take this into account. Now, I'm going to replace then the two transistors with two variable resistors or dependent resistances, which are fed by the current, and then of course the current will be split by the momentary value of these resistances. So here is the model, or the first part of it. First part of it is the two current sources. These are current sources. It's ABMI called in SPICE. ABMI is current sources, and they are defined here. This is the definition here. I've just rewritten here. It's the voltage across the device. This is the voltage, because this is a voltage with zero voltage on it, so there's no voltage here. So this is the voltage of the device, VD, divided by this expression. These are constant, which are defined in a parameter list, I'll show in a minute, times the temperature of the junction. Now, the temperature of the junction here is coded into a voltage. That is, I'm going to have later on, you'll see it, a node that has a voltage which is representing the temperature of the junction. So this is now the resistance, RDS on, and this current source now represents this resistance, and of course I'm approximating the RDS on by this straight line. Now these sources are, it's conventional way in SPICE, actually these are current sensor, you might say. I use for current sensing because in SPICE you can refer to the current of V1 or to the current of V2. That's a very classical way in SPICE, so therefore I've added these so I can refer to the current through it, which is the current here, of course. Okay, and then we have the other part, which is the thermal part, and then we have two current sources, which are representing the power, or actually dissipated by the device. This is the total thermal resistance. This is the ambient temperature, it's a voltage. And now the definition of these current sources, the power, is of course, first of all, the static power, which is the current, say I1 of one transistor times the voltage across it. I1 is IV1, that is the current through V1. Let's have a look at it. The current through V1 is defining I1. And then plus the approximation of the energy per switching cycle, which is, I've approximated this curve here, this one here, to this line here. So these are the coefficients. Here I have them. Times frequency, which is also a parameter. So this is the conduction losses, and these are the switching losses. And then we have these two transistors with the power passing through there, assuming the same thermal resistance. And obviously, this will be here now, the voltage here, this is the voltage here, will represent the temperature of the junction of this transistor, and this is the temperature of the junction of this transistor. Okay, so let's have a look then on the parameters that I have here. The ambient temperature, I've assumed 50 degrees. These are the coefficient of the linear approximation of the RDS(on) as a function of temperature. This is the thermal coefficient or resistance between junction and case, and ambient as a matter of fact, including everything. And this is a parameter which sort of makes a difference between RDS(on) of one transistor and another, because I like to see how is the difference if the initial value is different. So P is 1.5, like one RDS(on) is 40% more than the other one. And then we have the coefficient for the approximation for the energy per switching cycle, and frequency is defined in this particular case as 100 kilohertz. So these are the parameters that I used in the run. So here are one example of the results. Now what we see here, everything is a function of the current, the total current, okay? So it's starting from 0 up to 100 amp. We see now the splitting of the two currents. It starts at low current about 1.25. This is because of the 40% difference I've made. And then it actually goes down a little bit, not much, but at say 100, it's already, well, it's 1.2 or something like that, okay? So it's changing, but not drastically. Now, temperature of the two junction, of course, goes up here, and at 100 degrees, it's about 120, 100 amp, it's about 120. This is now the difference between the junction. This is the most important parameter here, because this is what we don't want. We don't want a difference in the temperature of the junction. And we see that at, say, 100 amp, it's already 10 degrees, okay? So this is, and of course, at the beginning, there's no difference because it is the temperature of the ambient. With no current or very little current. As the current is building up, then of course it is going up. And then we have the RDS(ons, here the two RDS(on), how they are changing with the current, because it's heating up, they're changing. And these are the actual current of I1 and I2. Another very interesting look is when I'm changing the scale here to temperature. This is now representing temperature of the junction of the first transistor, okay? So this is not volt, it's temperature, representing temperature. So I'm starting with 50 because this is the first point, it's the ambient, with the current is very low. And then at this point, the ratio of I1 and I2 is again 1.25 approximately. Now here we see the two temperature as they go up, as they build up. Of course, one of the curves is a straight line because this is the same, this is the temperature of the first transistor, one of the transistor. The other one is deviating from it. I've here now plotted the current, the total current, okay? Because this is now temperature, and I'm showing now for 120 degrees, what is the total current, and it is about 100 degrees, I guess, 95 amp, sorry. And then we see the temperature difference here for 100 centigrade junction potential of one of the transistor. The difference here is, well, at 8, 7.5 actually degrees centigrade, okay? This at 100 degrees, it's only 7.5 centigrade. Obviously, as it goes out to higher current or higher temperature, then it goes, the difference, of course, is increasing to, say, 10 degrees. This is now the RDS(on) and the second RDS one as a function of temperature. These should be straight lines because this is the linear approximation, and this is the current itself. So this is now for the set of parameters that I've shown earlier. Now I'm going to change one of the parameters. I'm going to change the slope that was 0.15 milli, actually it should be here, milli, to a much lower slope. So it's almost a straight line. And here what I am getting. So let's just concentrate on the 100 degree. This again in degrees centigrade. 100 degrees, I have now 1.36. Earlier, I had at 100 degree 1.2. This was 1.2. So I see that already there is a big difference, and this is because I don't have this positive temperature coefficient to correct. And then I see that at 100 degree, I have 11 degree of centigrade difference, while here I had only 7.5. So this also shows up in the most important parameter, the temperature of the junction. Okay, so now I'm going to change back to the original curve with the original, I'm sorry, this is the original slope. 0.15 should be milli here. Let me write here. This is milli. And but I'm going to increase the frequency so that the proportion of the power dissipated due to switching is becoming much larger. We've been at 100 kilohertz, now we are at 500 kilohertz. And what we see here is that obviously it's heating up faster. Here is 100 degrees, this is 100 degrees, and this is already for only 50 amp. Earlier it was for 100 amp. So here at 100 degrees, I already have a temperature difference between the junction of 5 degrees, and that's at fairly low current of 50 amp. So we see that as the balance between the power dissipated by RDS1 and the switching energy loss is changing, then of course the picture is changing completely. This brings me to the end of this presentation. I thank you very much for your attention. I hope you found it interesting and perhaps it will be useful to you in the future. Thank you very much.